If you pick up a heavy stone and hurl it into the sky, you already know exactly how the story ends. It goes up, slows down, and eventually yields to gravity, plummeting back down into the dirt. This intuitive downward pull is simply universal. In the late 16th century, Galileo Galilei demonstrated that all objects, regardless of their mass, accelerate toward the Earth at a constant rate. Naturally, the harder you throw that stone, the greater its initial speed, the higher the arc it traces before falling. But as thinkers like Nicholas Copernicus shifted our perspective from an Earth-centered solar system to a sun-centered one, a new question emerged. Is there a physical limit to that arc? A specific speed where an object is thrown so fast that it breaks free from the planet's gravitational grip entirely and never comes back? Yohida allowed Isaac Newton to formulate his universal law of gravitation in his landmark text, Principia. By combining Newton's mathematical laws with the principle of energy conservation, we can calculate the exact speed required to leave Earth behind. Any launched projectile is caught in a tug-of-war between two forces. Pushing it up is its kinetic energy, the energy of its motion. Pulling it down is gravitational potential energy, the energy stored by virtue of its position within Earth's gravitational field. To escape that downward pull, the projectile must travel so far that Earth's gravitational influence drops to zero, an infinite distance. To find the minimum effort required, the object must coast into infinity with its kinetic energy completely exhausted, dropping to exactly zero. We write this as a mathematical balance sheet. The total initial energy, kinetic minus potential, must equal the total final energy. Since the final energy at infinity is zero, we set the entire initial equation to zero and isolate our starting velocity. When we launch from the exact surface of the Earth, the starting height is zero. The algebra simplifies beautifully. Velocity equals the square root of 2 times the acceleration due to gravity times the radius of the Earth. We know Earth's gravity accelerates objects at roughly 9.8 meters per second squared. We know the radius of the Earth is about 6,400 kilometers. If we plug those specific numbers into the equation, we get 11.2 kilometers per second. That is the literal speed limit of Earth's gravity. Launch a rocket any slower, and it falls back. Hit 11.2 kilometers per second, and you break the chains permanently. But an isolated planet is a theoretical luxury. In the actual solar system, planets and moons are constantly competing for gravitational dominance. Consider two solid spheres locked in space, one with mass m, the other 4m, separated by a distance of 6r. Firing a projectile from the smaller sphere, it only needs enough speed to reach the neutral point where both gravitational pulls cancel out exactly. Drift even a fraction of an inch past that exact neutral point, and the larger sphere takes over. In deep space, you don't always have to outrun gravity entirely. You just have to coast far enough to let another world reel you in. This strict mathematical threshold actually answers one of the most visible cosmic mysteries in our night sky: why Earth has a thick, breathable atmosphere, while the Moon is a completely sterile vacuum. This chart shows the dramatic difference in gravitational strength between the two bodies. Because the Moon has a much smaller mass and a tighter radius, its escape speed is only 2.3 kilometers per second. That is roughly 1/5 the requirement of Earth. Out in the vacuum of space, extreme heat from the sun transfers kinetic energy directly to loose gas molecules. On the lunar surface, that thermal energy accelerates molecules past 2.3 kilometers per second, causing any atmosphere to rapidly leak into the void. Earth's atmosphere is heated by the exact same sun, but even at their most energetic, the vast majority of our oxygen and nitrogen molecules never get anywhere near 11.2 kilometers per second. Our planet's gravity is exactly strong enough to trap the air we breathe. That specific algebraic value, our 11.2 kilometer per second speed limit, is the physical foundation that keeps oceans from boiling away, allowing life to exist.